Hello and welcome back to the Science of Concrete Materials class. This is lecture number 9 of the class, and today we will continue our discussion on the cement module of the class. Today's topic is the Portland cement hydration. So far we have covered the hydration of the pure cement components in the previous lecture, and we stated that although this is not a true representation of what occurs to these phases within the cement as a whole, and although this is not entirely accurate, but it is a close approximation. Now we need to look at the hydration of the cement when all phases, in addition to the calcium sulfate, are present. So let's see the kinetics of the reaction. The rate of the reaction of the phases in the first few days are in the following approximate order. The C3A is the fastest, then followed by the C3S, C4AF, and then the C2S. It must be remembered, however, that none of these compounds will hydrate at exactly the same rate in different cements because their reactivities will be affected by the differences in fineness between the cements and the rate of cooling of the clinker. The rate of cooling is not constant for each batch of cement, so you have to remember. There will be additional factors such as the presence of impurities and the presence of other cement compounds. For example, the A-light and B-light hydrate faster than do the pure C3S and C2S. If you remember, the C3S in pure condition, we refer to it as the A-light and the C2S as B-light. This is because the impurity atoms contained in the structure of these phases. The hydration of the C3A and the ferrite phases are also affected by the impurity oxides present within them. If you remember in previous lectures, we mentioned that during the talk about the cement composition, that some of these phases, these phases will not be present in pure form as C3A or C3S. They will have impurities within them. So let's see what happened, or give examples of the compound interactions within the cement. The assumption made earlier that the cement compounds hydrate independently, as I said, is a reasonable one for most purposes, but is not entirely true. I re-emphasize that again. For example, C3A and C4AF both compete for the sulfate ions. But the more reactive C3A will consume more sulfate than does the C4AF. The effect of this to increase the reactivity of C4AF, since it forms less yttringite than would be expected. Okay. The gypsum increases the rate of hydration of the calcium silicates, which also compete for sulfate during hydration. It is known that the calcium silicate hydrate incorporates significant amounts of sulfate and also alumina and iron within its structure. So it has been estimated that the quantity of sulfoaluminates that forms in a paste may be less than half of the theoretical quantity calculated from the compound composition of the cement. This because of the interaction of the compounds, as the example I just mentioned. Another example, also the existence of an optimum gypsum content for the development of the maximum strength in a cement paste. I will explain. One explanation is that if a too high of a gypsum content will result in the formation of excessive amounts of ettringite, after the paste has hardened, which will cause unrestrained expansion and disruption of the paste microstructure. Whereas when we have too low of a gypsum content, this allows the monosulfoaluminate's solid solution, if you remember I showed this in the previous lecture, to form before the end of stage 2 of the C3S hydration, so that the resulting consumption of lime prevents the nucleation of the hydration products of C3S, which will delay stage number 3. Another explanation, though, suggests that gypsum accelerates the C3S hydration, but at the same time it lowers the intrinsic strength of the calcium silicate hydrate due to the presence of sulfate ions within its structure. So since there is a different gypsum content for maximum strength at different ages, both of these explanations may contribute to this phenomenon. Okay. The interaction between the calcium silicate hydrate and sulfate ions, may help explain the observation that there is also an optimum gypsum content for minimum drying shrinkage. And this optimum content for drying shrinkage may not be the same, or is not the same as for strength. So there has to be a balance. There has to be some experiments conducted in order to verify this optimum gypsum content. As you can see here, for example, strength versus gypsum content. At lower gypsum content, lower strength; at higher gypsum content, lower strength. So there is an optimum content. The same thing for drying shrinkage. Higher drying shrinkage for low gypsum content, and higher drying shrinkage again for too high of a gypsum content. So there is an optimum. Okay. Okay, I'm going too fast here. I'll go back. Okay, so you remember, let's talk about the heat of hydration. So you remember this graph, which is the heat of hydration curve for Portland cement I showed during the talk about the heat of hydration calorimetry. And the heat of hydration, we discussed during the talk about the hydration of C3S and C3A. This curve, is the heat of hydration curve for Portland cement. And notice how it looks analogous to the C3S curve. But before we talk about the details of this curve, I want to mention and reiterate, certain points about the heat of hydration curve, the science behind it, its significance and its practical importance. Don't worry, I will describe all these stages in detail and what happened at the end of each stage or during each stage. Okay, so the compounds of the Portland cement, as we mentioned before, are non-equilibrium products of high temperature reactions. And, therefore, they are in a high energy state. So when the cement is hydrated, the compounds react with water to acquire stable low energy states. And the process is accompanied by the release of energy in the form of heat. In other words, as we explained all along, the hydration reactions of Portland cement compounds are exothermic. So the heat of hydration can, sometimes be a hindrance, if you remember, especially when we are dealing with mass concrete structures or sections. And other times it may help, especially in winter concreting, or when ambient temperatures may be too low to provide the activation energy for the hydration reactions. Okay, the total amount of heat liberated and the rates of the heat liberation from hydration of the individual compounds can be used as indices of their reactivity. And we touched upon this before. I discussed before the data from the heat of hydration studies can be used for characterizing the setting and hardening behavior of the cements, and also for predicting the temperature rise. So the total temperature rise is important, as discussed above, and as we mentioned during the talk about the cements types and their uses. If you remember, the ASTM specifications put limits on the cement composition and or on the amount of heat of hydration. Examples, the ASTM C150 standard specification generally produce 330 to 370 kilojoules per kilogram, okay, in 7 days. The ASTM C150 contains, standard specifications for low heat Portland cement, which is type 4, and the moderate heat Portland cement type 2. With the 7 days heat of hydration limits of 250 kilojoule per kilogram and 290 for the moderate heat kilojoule per kilogram. Such Portland cements, as I mentioned, are no longer readily available, so there are other options. The hydraulic cements, meeting similar heat of hydration requirements, that is type LH, low heat cement, and the type MH, which is the moderate heat cement. Those can now be marketed under the performance specification ASTM C1157, which does not restrict the composition or the constituents of the cement. So it's just performance based. If it meets the heat generation requirements, then it is acceptable. Also, blended cements containing larger proportions of pozzolan, such as slag, can also satisfy the performance limits of the ASTM 1157. All right, this is just this what I said, I mentioned before, but I like to reiterate it just to relate the topics we discussed together. Okay, I will mention here, okay, before we move on, I will mention here the hydration products briefly, which we will discuss in more details later. So the hydration products of Portland cement, the calcium silicate hydrate, calcium hydroxide, the sulfo-aluminate phases, which is the yttringite and the monosulfo-aluminate. We have the aluminate hydrate phases and the calcium aluminate and or ferrite sulfate hydrate, or the calcium aluminate ferrite hydrate phases. This one here is another schematic showing the hydration process and what happens. As you can see, the hydration products I just mentioned. Right here, there's sulfo, the yttringite, and then the monosulfo-aluminate, which forms later due to the instability of yttringite in the absence of enough supply of sulfate. These are the calcium aluminate ferrite hydrate phases. This is the calcium hydroxide, and you see this is approximate. It shows the approximate formation of the approximate time of formation of these product from the beginning, since at the beginnings after the addition of water. And it also shows the various stages, the dormant period when setting occurs, which is the solidification, and the hardening, which is the strength gain. Okay, so this is, we will go over this again, but this is just a good schematic here. It shows you exactly what happens after we add the water, the dormant period, and the porosity, of course, goes down, and the hydration products begin to form. Okay. So, and this one here, basically the heat of hydration curve, and I added to it some SEM micrographs. It shows what happens at the end of each stage. For example, at the end of the dormant period, about 3 hours, the beginning of the nucleation of the calcium silicate hydrate. That will explain why we will have the initial set or the beginning of setting. And here the renewed reaction of C3S here, and here is the formation and for the more calcium silicate hydrate gel, where we will have final setting somewhere around here. So just as what I'm trying to do here, just relate what happened, what happens in the cement paste after we add water, what products form, and how it relates to this heat of hydration curve. Okay, so let's look at the mechanism of hydration and describe, what happened. As mentioned before, there is still much debate about the hydration process of Portland cement and the mechanism of formation of the hydration products. What is presented here, though, is the widely accepted theories regarding the hydration. Alternative theories, which with some differences in some of the details, based on recent research, exists, for those who would like to explore additional information. But I will present here what is reported in some of the textbooks, and I will show some more details from what is published in the literature. So if we look at the heat of hydration curve here, you could see these stages 1, 2, 3, 4, and 5. So what happens in each stage? See, look at stage 1, for example, which is the initial or pre-induction phase. It happens, between 0 to 15 minutes. Basically, shortly after water comes into contact with the cement, there is a sharp increase in temperature, which happens very quickly, within a couple of minutes. During this period, the primary reactive phases of the cement, are the aluminate phase, C3A, and possibly C4AF. The aluminate and ferrite phases react with calcium and sulfate ions to produce ettringite, which basically precipitates on the surface of the cement particles. During this phase, and to a lesser extent, the silicate phases, mainly the C3S, will also react in very small fractions, compared to their total volume, and form very thin layer of calcium silicate hydrate. So it becomes difficult for water to access the cement grains. Okay, phase 2, which is referred to as the induction or the dormant period. During this period, the rate of hydration significantly slows down and very, very little heat is given off. This is believed to be due to the precipitation of the aforementioned compounds on the surface of the cement particles, which leads to a diffusion barrier between these particles and water. Nevertheless, there is a significant debate regarding the physical and chemical properties behind the occurrence of this stage and the methods to predict it. What is the significance, of this, stage? During this period, fresh concrete is transported and placed. At this time, the concrete has not yet hardened and still workable, in plastic and fluid stage. The length of the dormant period has been shown to vary depending on multiple factors, such as, cement type. If you remember, we said type 3, which is the early strength cement, for example, the cement type, admixtures, if there is accelerating or retardant admixture, the water cement ratio, the presence of pozzolans, many factors. The end of the dormant period is typically characterized by the initial set. So that's one thing you need to remember. Okay, moving on. In stage 3, which is in about 3 to 4 hours to 10 hours, and we have stage 4 between 10 and 24 hours. This is the strength gain. In this phase though, in stage 3, the concrete starts to harden and gain strength. So the heat generated during this phase can last for multiple hours and is caused mostly by the reaction of the calcium silicates, mainly C3S and to a lesser extent C2S. The reaction of the calcium silicates, creates the second stage, calcium silicate hydrate, which is, the main reaction product that provides strength to the cement paste. Depending on the type of cement, it is possible to observe a third lower heat peak from renewed reactivity of C3A. Let me go back and show this. This here, right here, the small peak you see, okay? Okay, in stage 4, we call it the slowdown period. As the thickness of the hydration products increase and due to the decline of the unhydrated material, the process becomes diffusion controlled. The hydration process is said to be diffusion controlled when the coating covers the C3S grain formed by layers of the calcium silicate hydrate, which put a barrier through which the water must flow to reach the unhydrated C3S, for its hydrolysis, and through which ions must diffuse to reach the ground crystals. I talked about this, if you remember, during the hydration of C3S. Okay, then we have stage 5, or referred to as the steady state. At this point, the temperature of the concrete stabilizes with the ambient temperature. The process is completely diffusion controlled. The hydration process will significantly slow down, but will not completely stop. As long as there is water, that's why curing is important, guys. So remember that. The idea of studying this is to relate it to practical purposes and what you see in the field out there, how the concrete behaves. The idea is to relate it to the science behind it. Okay? So hydration can continue, as I said, for months, years, or even decades, provided there is sufficient water and free silicates to hydrate. That's why, again, curing is important. But strength gain will be minimal during this period. There will be strength gain, but minimal. Nonetheless, it continues to hydrate. Okay, with regard to the diffusion control though, some other researchers believe the slowdown is due to the unavailability of space for growth of calcium silicate hydrate gel needles, not entirely due to the diffusion control process. Okay, so here on this slide, shown additional information regarding the mechanism of hydration of cement. This is after Professor Scrivener, which is a world-renowned cement scientist, and she has many. She contributed to the advances of the cement chemistry and the concrete industry in general. Okay, so let's look at those and describe them just to relate this to what I have described above. If you look at these figures, according to this theory by Professor Scrivener, if you look at it, see figure A right here, which shows a section of an unhydrated cement grain with the phases present, C3A, C3S, and the ferrite phases, for example. Of course, these are exaggerated, but this is a good representation, and I really wanted to show it because it shows a lot and drives the point. Okay, so the following mechanism, of hydration happen, in the first few minutes of hydration, as you see in figure B right here. The aluminum and iron phases react with gypsum to form an amorphous gel at the surface of the cement grain. Okay? And short rods of ettringite grow, as you can see here, these short rods and this thin layer of gel, the amorphous gel that take place. Okay? After this initial period of reactivity, cement hydration slows down and the induction period begins. After maybe, let's say, about 3 hours of hydration, the induction period ends and the acceleration period begins. During the period from 3 to 24 hours, about 30% of the cement reacts to form calcium hydroxide and calcium silicate hydrate. The development of the calcium silicate hydrate in the period, that occurs between the development of the calcium silicate hydrate, occurs in 2 phases in this period. Okay, after roughly 10 hours of hydration, as you can see in figure C right here, C3S, has produced what is referred to as the outer calcium silicate hydrate, which grows out from the ettringite rods rather than directly from the surface of the C3S particles. Okay, so therefore, in the initial phase of the reaction, the silicate ions must migrate through the aluminum and iron-rich phase to form calcium silicate hydrate. That's what is referred to as the outer calcium silicate hydrate. Okay? In the later part of the acceleratory period, which is stage 3, after let's say 18 hours of hydration, C3A continues to react with gypsum, forming longer ettringite needles. As you can see here, this is referred to ettringite needles. Okay, this network of ettringite and the calcium silicate hydrate appears to form what is referred to as a hydrating shell, about 1 micrometer from the surface of the anhydrous C3S grain. Okay, so right here it appears to be as reported or as represented by this schematic. Okay, a small amount of inner calcium silicate hydrate forms inside the shell. As you can see, this is the inner calcium silicate hydrate. After 1 to 3 days, in this figure E right here, after 1 to 3 days of hydration, reaction slows down and the deceleration period begins, which is figure E, as I said. The C3A reacts with ettringite to form the monosulfate, as you can see here. The inner calcium silicate hydrate continues to grow near the C3S surface, narrowing this 1 millimeter gap between the hydrating shell and the anhydrous C3S. As you can see, this is the inner calcium silicate hydrate, narrowing this gap between the anhydrous C3S and the shell. The rate of hydration, again, is likely to depend on the diffusion rate of water or ions to the anhydrous surface. Okay? And like I said, according to Scrivener, the slowdown is caused by the limiting growth of the calcium silicate hydrate needles rather than the diffusion coefficient. Okay. After about 2 weeks of hydration, as you can see here in figure F, the gap between the hydrating shell and the grain is completely filled with this calcium silicate hydrate, and the original, outer calcium silicate hydrate becomes more fibrous, as you can see. Okay. So this is really a good representation of what happens during the hydration of cement, from 0 hours from the time we add the water until the complete hydration. Not the complete, the majority of the hydration has happened at this age. Okay. This here is also a schematic I wanted to show. Basically, it's a good representation of what happens after the addition of water, and what are the changes that occur to the cement grains and the growth of the hydration products, as you can see right here, and the changes in the properties of the hydrating cement paste or concrete. As you can see, these are cement grains. What happened, this coating around these grains, the dormant period occurs, where the reaction slows down. We end up here with the initial set at the end of after the end of the dormant period. It shows you here, this is limits of handling with the concrete for transporting, placing and finishing. It shows you here where the final set occurs and where the rigidity started to take place, the hardening of the concrete. So this is just a good representation to further re-emphasize the point. Okay, these are scanning electron microscope SEM photos that shows the development of the hydration products. And again, I'm showing them to just emphasize and corroborate what was discussed above about the hydration process. As you can see, for example, here, this is a photo showing the ettringite needle forming and the monosulfoaluminate phase. This photo here shows the hydration of the C3S, shows a hydrated particle, and shows, for example, this outer product we talked about, and the inner product, how this is denser than the outer product. These are the pores. And again, more photos, if you look at this, shows the unhydrated cement grain, the Portlandite, which is the calcium hydroxide. Here it shows really the distinction between the inner calcium silicate hydrate and the outer calcium silicate hydrate. Mark this by red pluses. This is the inner. Okay, and the outer, how you can see this is less dense than the inner calcium silicate hydrate. This is another photo here. It shows unhydrated cement grain, for example, and surrounded by a dense calcium silicate hydrate, which is the inner calcium silicate hydrate. We have monosulfoaluminate, as you can see here. We have calcium hydroxide shown, and the black spots here are these just the porosity. So not all space is filled. We will end up with pores, as you will see later. More photos here. This is just that shows the fibrous amorphous nature of the calcium silicate hydrate, again taken under scanning electron microscope. This is a 7 days old paste. It shows the calcium silicate hydrate all over the place. It shows the ettringite needles and the monosulfoaluminate in some places right here. Okay, so this is very powerful stuff that you can see with the micro scanning electron microscope. Okay, so I will stop here for this lecture, and next lecture we will start the discussion about the hydration products and the properties of the hydration products in more details. Okay, thank you for watching, and I will see you next time.